Welcome to Wisdom Docs. Settle in. Let the lights go low, let your shoulders drop away from your ears, and let your breathing find its own slow rhythm, the kind of rhythm the tide keeps without ever being told to. There is nothing here you need to solve tonight. There is nothing you need to hold on to. All you have to do is drift and let the story carry you the way deep water carries a small boat, gently, patiently, without hurry. Tonight we are going to travel to the bottom of the ocean. Not the shallow, sunlit bottom near the shore, where the sand ripples and the fish flash silver. We are going far deeper than that, and far farther out, into a part of the world that almost no eyes have ever seen directly, a place of permanent darkness and immense, cold quiet. And down there, on the floor of the largest ocean on Earth, there is a trail. A long, long trail of dead volcanoes. And that trail has a bend in it. A sharp, strange, almost impossible bend that no one could fully explain for 50 years. Picture it slowly, because we have all the time in the world. Imagine a line of mountains, more than 80 of them, running across the floor of the North Pacific. Some are still islands you could stand on. Most are not. Most are drowned now, worn down and sunk beneath the waves, their summits hundreds or even thousands of meters below the surface, wrapped in that endless dark. And this line of mountains does not run for a mile or 10 miles or 100. It runs for roughly 6,000 kilometers. About 3,700 miles. That is the distance across a continent. A single, connected chain of volcanoes stretching from the warm, living, glowing island of Hawaii in the southeast, all the way to the cold northern edge of the Pacific, up near the coast of Kamchatka, where it finally slides down into a deep ocean trench and disappears. 6,000 kilometers of volcanoes laid down one after another like footprints. And somewhere along that enormous trail, a little more than halfway up, the whole line suddenly changes direction. It turns. Not a gentle curve, not a lazy drift the way a river wanders across a valley. It turns hard, by about 60 degrees, a genuine elbow, a kink, as if the trail were being drawn by a steady hand that abruptly changed its mind. Below the bend, the chain runs off toward the west-northwest. Above the bend, it shoots off almost due north. Two long, nearly straight limbs meeting at one sharp corner on the floor of the sea. And for half a century, that corner was one of the most quietly famous puzzles in all of earth science. Because here is the thing I want you to hold in the back of your mind as you drift, the loose thread we are going to follow all the way through this story. There was an answer to the bend. A beautiful answer. A simple, elegant answer that seemed to explain everything. That seemed to fit so perfectly that scientists built entire ideas about how the planet works on top of it. And then, in the year 2003, a team lowered a drill through kilometers of ocean and bored down into a lava that was 76 million years old. They pulled a piece of that ancient rock back up into the light, and the rock told them something that quietly took the beautiful answer apart. It told them that the one thing everyone had assumed could not move had in fact been moving all along. But we will get there. We have a long, gentle way to go first, and there is no reason to rush toward the ending. Let it come to us slowly, the way morning comes to a harbour, one soft shade at a time. So let us go back to the trail itself and walk it in our minds. This chain has a name, and the name itself carries the story of the bend, because the two halves are named separately. The whole thing together is called the Hawaiian Emperor Seamount chain. Say that softly to yourself. Hawaiian and Emperor. Two names for the two limbs that meet at the corner. The southern limb, the one closer to Hawaii, is called the Hawaiian Ridge. That is the limb that runs off toward the west-northwest. If you have ever seen a map of the Hawaiian Islands, you already know the very beginning of it. The Big Island, then Maui, then Oahu with its city and its beaches, then Kauai, all of them strung out in a line, heading up and to the left toward the northwest. But those bright, famous islands are only the youngest tip of something enormous. Keep following that line, past Kauai, past the smaller islands, past the little scattered reefs and shoals that most people have never heard of, and it just keeps going, sinking lower and lower beneath the water, a ridge of drowned mountains marching on for thousands of kilometers into the empty middle of the ocean. That whole underwater ridge and the living islands at its tip together make up the Hawaiian Ridge, the west-northwest limb of the chain. And then you reach the corner, the bend. And once you round that corner, the chain changes its name and its direction both at once. Now it is called the Emperor Seamounts, and instead of heading west-northwest, it turns and runs almost straight north, only very slightly leaning to the west, aiming up toward the far cold corner of the Pacific near Russia. The word seamount simply means an underwater mountain, a peak that rises from the ocean floor but never quite reaches the surface, or once did and has since sunk back down into the dark. And the Emperor Seamounts are exactly that, a long procession of drowned peaks, no islands left among them at all, every single one of them beneath the waves, running north toward the Aleutian Trench. They carry the names of Japanese emperors, these northern seamounts: Meiji, Nintoku, Jing, Jin, Jimmu, Suiko, names given to them by an American geographer named Robert S. Dietz back in 1954, long before anyone understood what the chain really was or why it bent. He looked at this line of hidden mountains marching up toward Japan and Kamchatka, and he named them for emperors, and the name stuck. So now we have this quiet poetry in the geography. The bright Polynesian islands with their soft flowing names down in the warm south, and the drowned imperial mountains with their formal names up in the cold north, and between them, joining the two worlds together, that single sharp elbow on the floor of the sea. And right at the elbow itself, right at the very corner where the trail turns, there are seamounts too, sitting at the hinge. Two of them are worth holding in your mind, because they mark the exact spot where west-northwest becomes north. One is called Daikakuji Seamount. The other is Kimmei Seamount. These are the seamounts of the bend, the mountains that sit in the crook of the elbow, the last of the Hawaiian Ridge and the first of the emperors, depending on which way you are walking. When scientists want to point at the bend, at the precise place where the mystery lives, these are the names they reach for. Daikakuji, Kimmei, the hinge of the whole 6,000-kilometer chain. Now, before we go any further, I want you to feel just how strange this trail is, because the strangeness is the whole reason it became a mystery. And the mystery is the whole reason it is worth a night's slow telling. Imagine you found a line of footprints crossing a wide, smooth field of fresh snow. The footprints run in a perfectly straight line, evenly spaced, for a very long way. And then, at one point, without any change in the field, without a fence or a wall or a stone in the way, the footprints turn sharply and set off in a new direction, again in a perfectly straight line, again evenly spaced. You would stop, you would stare at that corner, you would ask the obvious question. What happened here? What made whoever left these tracks turn? There is nothing on the ground to explain it. The turn came from somewhere else, from something you cannot see just by looking at the prints. That is the bend in the Pacific floor. A line of footprints across the ocean bottom, walking steadily along, and then, roughly 47 million years ago, turning hard. And the great question, the 50-year question, was always the same simple, stubborn one that you would ask standing over those footprints in the snow. What happened at the corner? What turned the trail? To even begin to answer that, we have to understand how the footprints get made in the first place. And here is where the beautiful, simple idea comes in. The idea I promised you, the one that seemed to explain everything. It is called the hotspot, and it works like a conveyor belt, and once you see it, you will understand why scientists fell in love with it. Picture, deep beneath the ocean floor, a single fixed column of hot rock. Not liquid exactly, not like the fire in a chimney, but rock so hot and rising so slowly that over the ages it behaves almost like a thick hot current welling up from far below. This rising column is called a mantle-plume, and where it reaches near the surface, it melts the rock above it and feeds a volcano. That place, that spot on the surface, sitting over the top of the plume, is called a hotspot. And the crucial idea, the whole heart of it, is this. The hotspot stays still. The plume is anchored deep down, rooted far below, and it does not wander. It is a fixed flame, burning up through the planet from somewhere far beneath, holding its position across unimaginable spans of time. But the floor of the ocean above it does not stay still. The great slab of rock that makes up the bottom of the Pacific Ocean, the piece of the Earth's outer shell that geologists call the Pacific Plate, is slowly, constantly on the move. It slides. Not quickly. Nothing about this is quick. It slides at a pace of roughly 7 to 10 centimetres a year. Let that number settle for a moment, because it is one of the quietest, most soothing facts in all of geology. 7 to 10 centimetres a year is about the speed your fingernails grow. Right now, as you lie here breathing slowly, the entire floor of the Pacific Ocean, a slab of rock big enough to hold a chain of mountains 6,000 kilometres long, is drifting along at exactly the unhurried pace of a growing fingernail. You would never see it. You could watch it for your whole life and never catch it moving. And yet it never, ever stops. So now put the two pieces together, the fixed flame below and the sliding floor above, and watch what happens, slowly, over millions of years. The hotspot burns up through the moving plate and builds a volcano. That volcano grows and grows, erupting again and again, until it rises up through the sea and becomes a high island, a mountain standing in the ocean. But the plate it is standing on is sliding at fingernail speed toward the northwest. So very slowly, over 1 million years or so, that island is carried away from the hotspot. It drifts off the flame, and once it drifts off, its fire goes out. It is cut off from the source of heat that made it, and it goes quiet and it goes cold. It becomes an extinct volcano, a dead island, riding away on the conveyor belt. And behind it, over the hotspot that has not moved, a new volcano begins to grow. The flame is still burning in the same fixed place. And now there is fresh plate sliding over it, and so it builds another mountain. And that one, too, in time drifts off toward the northwest and dies, and yet another is born behind it. Over and over and over, for tens of millions of years. A fixed flame, a moving sheet of rock, and roughly one new volcano built every 1,000,000 years or so, each one blazing into life over the hotspot, then being carried away to grow cold and sink. A conveyor belt of islands, a machine for laying down a trail, and do you see what that trail becomes? It becomes a record, a line of dead volcanoes marching off in the direction the plate is moving, with the oldest ones farthest from the flame and the youngest ones closest to it. The trail of footprints in the snow is exactly this. Each footprint is a volcano. The hotspot is the foot, staying in place and pressing down, and the moving plate carries each print away and presents fresh ground for the next. The chain of mountains is a diary of the plate's journey, written in stone, one page every million years. This idea did not come from nowhere, and it did not come easily. It was proposed by a Canadian geophysicist named Tuzo Wilson in 1963, and he proposed it precisely to explain Hawaii. He had noticed the thing that anyone who looks closely at the islands notices sooner or later, the thing we will follow in detail in a little while. The islands are not all the same age. They get older as you go northwest. And Wilson realized that a fixed source of heat, with the plate sliding over it, would produce exactly that pattern. This was a bold thing to say in 1963, because at that time the whole grand theory of moving plates, the theory we now call plate tectonics, was brand new and still being argued over. The idea that the solid ground could move at all was still radical, and here was Wilson, using this quiet chain of Pacific islands to argue not only that the plates move, but that beneath them sit these fixed, deep, stationary flames that the plates slide across. He was using the Hawaiian chain as a kind of yardstick, a fixed ruler against which the plate's motion could be measured. Then, in 1971, a scientist at Princeton named W. Jason Morgan took the idea further and gave it its deeper root. Morgan proposed that these hotspots are fed by narrow plumes of hot rock rising from very deep inside the mantle, from far, far down toward the center of the earth. And he pointed to the Hawaiian Emperor Bend as a keystone example, a showpiece, the clearest evidence you could ask for that plates ride over fixed plumes. Because look, he could say, look at the trail these fixed plumes leave. Look at the Hawaiian chain. And look especially at the bend. If the plate is what is moving and the flame stays still, then the bend in the trail must be the moment the plate changed direction. Below the bend, the plate was heading one way. Above the bend, it was heading another. The elbow on the ocean floor was, in this beautiful reading, nothing less than a fossil record of the day the Pacific turned a corner. And you can feel, I hope, how satisfying that is, how clean. The whole enormous, strange 6,000-kilometre trail, with its sudden hard turn, all of it explained by two simple ingredients: a flame that stays put, and a floor that slides and once changed course. Everything accounted for, every footprint, and even the sharp corner in the middle of them. For a long time, this was the answer. This was what the textbook said, what students learned, what seemed as solid as the seafloor itself. The plate turned, and the trail bent, and that was that. Hold that feeling of satisfaction, though, hold it gently, and hold it lightly, because this is the part of the story where I have to ask you to keep one small doubt alive in the back of your drifting mind. Remember, the whole idea rests on one assumption, one single assumption, sitting quietly underneath everything else, holding the whole beautiful structure up. The flame does not move. The hotspot is fixed. It is the still point, the anchor, the thing you measure everything else against. Every conclusion, every reading of the trail, every claim that the bend marks the day the plate turned, all of it depends completely on the hotspot staying exactly where it is. And that is the loose thread. That is the question I want to leave hanging over the rest of this story. softly, like a lantern swaying on a dock. The whole chain is a record of the plate's motion, measured against the fixed flame. But what if the thing it was being measured against was not fixed at all? What if the flame itself was moving? Not fast. Nothing here is fast. But what if, all through those long ages, while the plate slid along at its fingernail pace, the deep plume beneath it was also, quietly, drifting through the earth? What would that do to the trail? What would it do to the bend? And how could anyone, tens of millions of years later, ever hope to tell the difference between a trail bent by a turning plate and a trail bent by a wandering flame? Set that question down beside you. We are not going to answer it yet. It will take a drill, and a very old rock, and a kind of stone compass hidden inside that rock, before we can answer it honestly. For now, just let the question rest there in the dark, glowing faintly, while we go back and walk the trail again, more slowly this time, feeling the ages pass. Because to understand how anyone could ever have discovered that the flame moved, you first have to understand just how carefully the trail keeps time, and it keeps time astonishingly well. This is the thing that made Wilson certain in the first place, the thing that makes the whole conveyor belt more than just a pretty idea. The ages of the volcanoes really do increase, steadily and reliably, as you move away from Hawaii. It is not a guess. It is measured again and again in the rock itself. Start at the living end, the warm end, down at the Big Island of Hawaiʻi. There, the volcanoes are essentially newborn. Kīlauea, which still glows and flows today, and the summit of the Big Island, are somewhere between 0 and less than 1,000,000 years old. In the life of a planet, that is this very morning. The fire is still lit, the island is still being built. This is the youngest footprint, the one nearest the flame, the fresh print pressed into the snow just moments ago. Now step northwest up the trail to Kauai, the oldest of the main Hawaiian islands you might visit, the green and deeply eroded one. Kauai is about 5 million years old. Its fire went out long ago. The rains and the sea have been carving it for 5 million years, cutting those deep valleys and sharp ridges. It drifted off the flame 5 million years back, and it has been dying, slowly and beautifully, ever since. Keep going, farther up the trail, out past the last of the familiar islands, into the long stretch that most people never think about, and you come after a great distance to Midway Atoll. You may have heard the name for other reasons, for things that happened on its surface far more recently than any of this. But as a piece of the trail, Midway is about 28 million years old. 28 million years since it stood over the hotspot as a high volcanic island. And it is not a high island anymore. It is an atoll now, a low ring of coral around a quiet lagoon. The mountain that once stood there long, since worn down and sunk beneath the waves, with only a rim of living reef left to mark where its shores used to be. Midway is the trail in middle age, halfway between a fiery birth and a final drowning. Keep going still, all the way up to the bend, to those hinge seamounts, Daikakuji and Kimmei, sitting in the crook of the elbow. The bend is about 47 million years old. Say that number gently and let it stretch out in your mind. 47 million years. That is when the corner was turned, when the trail changed its heading, when whatever happened, happened, and I want to pause on this number for a moment, because there is a small, honest wrinkle in it that matters. For a long time, the older books gave a different figure for the bend. They said 43 million years. You may still see that number written down in places. but careful dating of the lavas near the elbow, using a precise method that reads the slow ticking of certain atoms locked inside the rock, has revised that figure. The bend is now placed closer to 47, perhaps 48 million years old. So if the old number and the new number ever seem to disagree, that is why. The trail is a little older at its corner than we used to think. We will use the corrected figure, 47 million years, and simply note that the earlier one has been set gently aside. But we are not at the end of the trail yet. Not nearly. Round the bend and start up the northern limb, up the drowned Emperor Seamounts marching toward the cold, and the ages keep climbing. Far up that northern line lies Detroit Seamount, and Detroit is old indeed, something like 76 to 81 million years old. This is deep time now, the age of the very rock that, one day, a drill would reach down and touch. And beyond even Detroit, at the very far northwestern end of the whole 6,000-kilometre chain, right at the edge of the Aleutian Trench, lies the oldest surviving link of all. Its name is Meiji Seamount, and Meiji is roughly 82 to 85 million years old. It is the last footprint, the oldest print still left in the snow. And here is the quiet, aching thing about Meiji, the thing to carry with you as this part of the story slows toward its rest. Meiji is not the beginning of the trail. It is only the oldest part we can still find, because the far end of the chain has reached the edge of the Pacific Plate, the place where that great sliding floor finally dives down beneath another plate and descends back into the depths of the earth, into the deep gash in the seafloor called the Aleutian Trench. And Meiji Seamount is being dragged down into that trench right now. The oldest link in the chain is, at this very moment, being pulled under and destroyed. Whatever volcanoes came before Meiji, whatever earlier footprints the flame once pressed into the plate more than 85 million years ago, they are gone, already swallowed, already carried down into the deep and unmade. The trail has no memory older than Meiji, not because the story began there, but because everything before it has already slid off the far edge of the world and vanished. So there it is, laid out before us in the dark. A conveyor belt of stone, 6,000 kilometres long. A fire being lit at one end, down at Kīlauea and the Big Island, this very geological morning. And a fire being extinguished at the other end, up at Meiji, as the oldest islands are dragged down into the trench and erased. The record is being written at one end and rubbed out at the other, continuously, patiently, at the speed of a growing fingernail, and it has been doing this for more than 80 million years. Kīlauea at 0, Kauai at 5, Midway at 28, the Bend at 47, Detroit at 76, Meiji at 82, sliding into the dark, a perfect line of ages, a diary in stone, kept faithfully across almost unthinkable spans of time. And through all of it, holding the whole reading together, sits that one quiet assumption we set glowing on the dock behind us. That the flame at the young end never moved, that the hotspot has always been exactly where it is now, that the trail is a true record of the plate's motion, and only the plate's motion, measured against a still and steady flame. Everyone believed it. It explained the ages. It explained the two straight limbs. It even explained the sharp and lovely corner in the middle, the bend, which it read as the fossil of the day the plate turned toward the northwest. But the doubt is still there, swaying softly in the dark behind us. What if the flame moved too? And far up the northern limb, near Detroit Seamount, in a lava that had lain undisturbed on the ocean floor for 76 million years, the answer to that question was already waiting. It had been waiting the whole time. It was locked inside the rock, frozen there on the day the rock first cooled. A tiny record of exactly where on the earth that lava had been born. All it needed was for someone to reach down through the kilometers of cold black water and drill into it and ask. To understand how anyone arrived at that answer, the one written in the ages of the stone, the one that seemed, for a long time, to explain everything. You have to go back to a man working at a desk in Canada in 1963, at a moment when the whole field of earth science was in the middle of being remade from the ground up. His name was Tuzo Wilson. He was a geophysicist at the University of Toronto, and he had been watching with the particular patience of a man who enjoys a good puzzle. The growing body of evidence that the floor of the ocean was not static, that it moved, that the continents, which had once been laughed at as preposterous for their suggestion of drift, were in fact being carried very slowly on plates of rock riding above a deeper, partially molten interior. This was the revolution of plate tectonics, and it was arriving in pieces. Sonar maps of mid-ocean ridges, magnetic striping patterns frozen into the seafloor, the dawning arithmetic of seafloor spreading, and Wilson was one of the people helping to fit the pieces together. But Hawaii bothered him. It bothered him in a specific, productive way. Hawaii sits in the middle of the Pacific Ocean, far from any plate boundary, far from any mid-ocean ridge, far from the volcanic edges where plates collide and one dives beneath another. It has no business being a chain of volcanoes. And yet there it is, and there the chain goes, all the way to the northwest. Island after island, seamount after seamount, each one progressively older, as if something had been sliding the plate over a fixed source of heat and printing volcanoes onto it, one after another, like a stamp pressed along the length of a moving ribbon. The elegance of Wilson's idea was that the hotspot, the source of the heat, did not need to be explained by any of the plate boundary processes geologists already understood. It was something else, something deeper. A stationary column of anomalously hot rock rising from far below the ordinary mechanics of plate movement, punching upward like a slow blowtorch, melting the underside of the plate as the plate slid over it. The plate moved. The blowtorch stayed still. And the result was a line of volcanoes whose ages told you, perfectly, unambiguously, exactly how far each one had been carried from the source, and therefore, if you knew the ages, how fast the plate was moving. This was Wilson's fixed-hotspot idea, offered as a brief paper in 1963, and it was, in the way of the truly good ideas, almost embarrassingly simple once someone said it out loud. A fixed flame under a moving sheet. One new volcano born from the flame, carried away, going cold and dark, while the next one grows in the heat it left behind. A conveyor belt, patient and slow, building a record of the plate's motion across millions of years of time. The Hawaiian Emperor Seamount chain, in this reading, was not a mystery. It was a diary. A precisely dated diary of where the Pacific plate had been, how fast it had moved, and when it had changed direction. The chain was the instrument and the readout at once. Wilson's paper was not immediately received with universal acclaim. In 1963, the plate tectonics revolution was still finding its footing, and a proposal that involved a deep-seated, stationary heat source in the mantle was speculative enough that it took years for the weight of evidence to accumulate behind it. But the idea was alive, and it found a powerful advocate. W. Jason Morgan was a geophysicist at Princeton, and in 1971 he published a paper that took Wilson's suggestion and made it structural. Morgan proposed that hotspots like Hawaii were not simply vague warm spots in the mantle, but were the surface expressions of narrow, deep columns, mantle plumes, rising from the very base of the mantle, near the boundary between the rocky mantle and the liquid iron outer core, roughly 2,900 kilometers beneath the surface. Not shallow anomalies, not local quirks. Deep, almost implausibly deep, reaching from something close to the heart of the planet up toward the crust. And he used the Hawaiian Emperor chain as one of his centerpiece examples, demonstrating that the geometry of the chain and its age progression were exactly what you would expect if the Pacific plate were sliding over a deep fixed plume at the rate of several centimeters per year. Morgan's paper connected the beautiful simplicity of Wilson's fixed flame idea to the broader framework of plate tectonics and gave it a physical mechanism, the plume, that could be imagined, modelled, and eventually searched for with the tools of seismology. Between Wilson in 1963 and Morgan in 1971, the foundation was laid for what would become one of the most powerful tools in all of geology, using hotspot chains to read the motion of tectonic plates across geological time. And the Hawaiian Emperor chain was the star pupil. Let the idea settle in for a moment, because it is worth fully inhabiting before any complication arrives. Imagine, far below the Pacific Ocean, below the cold water, below the sediment, below the basaltic crust, below the upper mantle, all the way down, almost to where the rocky mantle meets the liquid iron of the outer core, a column of rock slightly hotter than the rock around it. Not dramatically hotter in any explosive or catastrophic sense. Just enough hotter that it rises, very slowly, the way warm water rises in a pot, ascending through 2,000 kilometers and more of solid but slowly flowing rock, taking millions of years for the material to travel from the deep source upward to where the pressure is low enough and the temperature high enough that it melts and erupts. This column, the plume, does not move sideways. It stays rooted, or very nearly so, while the plate above it slides past. And the plate above it, the Pacific plate, the largest single piece of oceanic crust on Earth, is moving. Northwestward, at the pace Wilson and Morgan calculated, something between 7 and 10 centimeters per year, about as fast as a fingernail grows. An inch every couple of years roughly, if you need a human scale. Trivial in a lifetime. Enormous across 10 million years. As the plate slides, the section of crust directly above the plume receives the heat first. Rock melts. Magma rises through cracks and fractures in the overlying plate. Eruptions begin on the seafloor, building a pile of lava that grows upward, layer by layer, over hundreds of thousands of years, until eventually the pile breaches the surface of the ocean and an island appears. The island grows taller as eruptions continue. But the plate keeps moving, carrying that island away from the heat source underneath it, the way you might slowly drag a piece of paper across a candle flame. The paper carries its burn marks away, and the flame waits for the fresh paper behind. As the island drifts off the hotspot, the eruptions slow and then stop. Without the heat source feeding it, the island's volcanic engine goes quiet. And then, slowly, over the next several million years, something else begins to happen, something Darwin described nearly 2 centuries ago, from observations made in the Pacific and the Indian Ocean, on a very different kind of voyage. Charles Darwin spent years at sea, and the coral atolls of the tropics puzzled him. They are rings, rings of reef and low sandy island, sometimes enclosing a quiet lagoon, sitting in open ocean with no obvious foundation beneath them. How did they form? Where did the reef have to grow from? Darwin's answer, published in his 1842 book on coral reefs, was that atolls were not original rings. They were the last remaining visible evidence of islands that had sunk. A high volcanic island rises from the sea. Coral establishes itself around the island's shores, building a fringing reef in the warm, shallow water close to land. Then, slowly, over millions of years, the island subsides. The crust beneath it cools as it moves away from whatever heat was supporting it, and it contracts, and it sinks. The coral reef, which can build upward as fast as the island sinks, keeps pace, growing taller to stay in the sunlit shallow water while the volcanic rock it grew on disappears beneath it. Eventually, the island is entirely gone, swallowed by the sea, and all that remains above the surface is the reef, the ring, the atoll, sitting in the middle of the ocean as if it had always been a ring, a hollow crown in the water. Darwin did not know about mantle-plumes. He did not know about hotspots or seafloor spreading. But his subsidence theory of coral atolls was correct, and the Hawaiian chain is the most complete demonstration of it that exists anywhere on Earth. Every stage of the life cycle is represented somewhere along the chain's 6,000 kilometers, arranged in order of age, like a textbook laid out across the ocean floor. At the young end, the southeast end, you have the Big Island of Hawaiʻi, a massive, active, growing volcanic pile, still being fed by the heat below, with Kīlauea erupting and Mauna Loa capable of erupting, rising nearly 14 kilometers from the seafloor to the summit if you measure from the base. This is the island in its youth, raw volcanic rock, minimal soil, lava flows still reaching the sea in living memory, the island adding new land to itself even now. A few million years back, which means a few hundred kilometers to the northwest, you have Maui and the older islands of the chain, where the volcanoes have gone quiet, but the mountains are still high, still steep, still clothed in rainforest, fed by trade winds lifted over the peaks. The volcanic fires are out, but erosion has not yet had time to finish its work. The land is still substantial. Further northwest still, about 5 million years old, sits Kauai, older, lower, its ancient volcanic vents long silent, its mountains worn and rounded by the relentless work of rain and rivers, the Napali cliffs carved into what was once a much higher and less dramatic coastline. Fringing reefs have given way to barrier reefs growing in the warmer water offshore. The subsidence Darwin described has already begun. Move northwest again, another 100 or so kilometers, through a deepening series of smaller islands and shoals, and you approach the middle of the chain. Islands that still sit just above sea level, but are no longer real islands in the sense of offering solid volcanic mountains. They are low, sandy, reef-built places, the coral crowns of peaks that have sunk so far beneath the surface that only the reef keeps them visible. French frigate shoals, Laysan Island, Pearl and Hermes Atoll, each one a former high volcanic island, now a coral ring. And then, about 28 million years old, sitting in the middle of the North Pacific, you reach Midway Atoll. Midway is the most famous of the Hawaiian chain's elder citizens, known mostly in the wider world for the battle fought nearby in 1942. But for the purposes of the chain, it is something more quietly remarkable. It is a nearly perfect example of exactly what Darwin's theory predicted. 2 small sandy islands and a surrounding coral reef, enclosing a shallow lagoon, the last above-water evidence of a high volcanic island that was once 28 million years ago, roughly where the Big Island stands today, growing over the same hotspot, erupting the same kind of basaltic lava built by the same deep flame. Now Midway sits low and level with the sea, the coral reef standing in for the island that has entirely sunk. The volcanic rock is there, but it is far below the atoll, buried under the reef it once supported. And northwest of Midway, past the last small atolls and shoals, the chain disappears below the surface entirely. The islands are gone. What continues is a line of drowned peaks, seamounts, rising from the seafloor, but not far enough anymore to reach the surface. These are the giots, flat-topped underwater mountains whose summits were once islands, planed flat by wave erosion during their time at sea level, then carried downward as the crust sank beneath them, the flat tops preserved underwater like photographs of a shoreline that no longer exists. The name Giot, pronounced Gui-o, comes from Arnold Henry Giot, a 19th-century Swiss-American geographer, though it was applied as a geological term in the mid-20th century. And in the Hawaiian chain, the gyots begin roughly where the atolls end, continuing the march northwest, each one dipping progressively deeper as the crust carrying it grows colder, denser, and more thoroughly sunken. This entire progression, erupting volcano, high island, fringing reef, barrier reef, atoll, drowned gyot, is Darwin's theory played out in real time, across a single connected chain, laid out like a film strip across the floor of the Pacific. Each island is a different frame in the same movie, and the movie runs from youth to old age as you move from southeast to northwest. Wilson and Morgan did not just explain why the volcanoes were there. Their model, combined with Darwin's subsidence idea, explained every stage of what happened to those volcanoes afterward, from the moment they broke the surface to the moment they disappeared beneath it. Now, the bend, the corner, the elbow that sits at the juncture of the Hawaiian Ridge and the Emperor Seamounts, near a pair of underwater peaks called Daikakuji Seamount and Kimmei Seamount, at roughly 47 million years of age. In the classical reading, the reading that Wilson and Morgan's model seemed to demand, and that most geology textbooks for the last several decades have faithfully delivered, the bend records a moment. A specific moment in geological time, around 47 million years ago, when the Pacific plate changed its direction of motion. Before that moment, the plate was moving roughly northward, and the hotspot was printing a trail of volcanoes in that direction, the Emperor Seamounts, nearly north-south, pointing toward the Aleutians. After that moment, the plate shifted and began moving northwestward, and the hotspot printed the Hawaiian Ridge, the southeastern limb of the chain, the one that contains all the familiar Hawaiian islands. The corner between the two limbs is the fossil of the turn. It is a remarkably satisfying explanation. One moment, frozen in stone, a 60-degree rotation in the direction of the world's largest tectonic plate, recorded faithfully by a fixed flame that had no say in the matter. A geological event horizon. Before the bend, north. After the bend, northwest. The bend itself, the exact moment the plate made up its mind. And the numbers agreed. The rate of plate motion inferred from the spacing and ages of the Hawaiian Islands matched the rate inferred from the Emperor Seamounts. The geometry was consistent. Everything fit inside a single elegant framework. The Pacific plate had been moving over a fixed hotspot for more than 80 million years, first northward, then northwest, and the kink in the chain was the boundary between the two chapters. The chain was a timeline, and the bend was a comma in the middle of it. This is the story that entered the textbooks, and not without reason. It was genuinely powerful. It was supported by the age dates. It was consistent with the rates of plate motion calculated from other methods. It gave the Hawaiian Emperor Seamount chain a role as one of the founding pieces of evidence for the theory of plate tectonics, one of the clearest demonstrations that plates move, that they move at measurable rates, and that they can change direction in geologically detectable ways. And it let the chain do something extraordinary. If the hotspot is fixed, and the chain records only the plate's motion, then the chain is a kind of instrument, not just a record of the past, but a measuring device. You can read the chain's geometry and ages and calculate, with some precision, how fast the Pacific plate moved at different periods over the last 80 million years. You can even infer from the direction of the chain's two limbs which directions the plate was travelling at different times in its history. The chain becomes a speedometer and a compass for the plate's entire recorded life. That is how confident the field became in the fixed hotspot idea. Confident enough that the chain was used not just as evidence for the idea, but as a calibration tool, a known fixed reference from which other things could be measured. And for roughly 30 years, from the early work of Wilson and Morgan through the 1980s and into the 1990s, the picture held together well. The Hawaiian Emperor Seamount chain was the most famous example of a fixed hotspot track in the world, and the bend was its most famous feature, the corner that proved the plate had turned. The chain's age progression has a kind of music to it if you let it wash over you slowly. Kīlauea, erupting now, essentially 0 years old, standing at the southeastern tip of the Big Island and adding its lava to the Pacific daily. Kauai, 5 million years quiet, its volcanic mountains softened and green. Midway, 28 million years at sea, a white and blue atoll floating in the deep ocean. The Bend, 47 million years old. A corner in the seafloor no one can see from the surface, an elbow on the silent floor of the Pacific. Detroit Seamount, 76 million years old, drowned hundreds of meters below the surface, its flat top a testament to the wave erosion it endured during its time as an island long before human civilization appeared on Earth. And Meiji Seamount, 82 million years old, the oldest surviving piece of the chain's record, now being slowly consumed by the Aleutian Trench, the deep gash in the seafloor where the Pacific plate dives beneath the plate that carries Kamchatka, taking the old record with it into the mantle, erasing it. Everything older than Meiji is already gone, not hidden, not simply deeper. Gone, subducted, carried down into the mantle by the motion of the plate, returned to the interior, the rock recycled, the age record destroyed. The chain may once have been much longer. There may have been seamounts with ages of 90 million years, 100 million, perhaps more. Volcanic products of the same plume that has been burning since before the breakup of Gondwana. But we will never know what they were, because the plate that carried them has already made the one-way trip down into the mantle, and anything they had to tell us has been unmade. The chain, then, is both a record and a demonstration of its own impermanence. It is being written at one end, Kama e Huakanaloa, the submarine volcano still building itself in the dark beneath 1,000 meters of Pacific water, southeast of the Big Island, the next island in the chain that will not break the surface for tens of thousands of years, but is already accumulating the lava that will eventually get it there. and it is being erased at the other end, where Meiji slides toward the trench. Between those 2 points, across 6,000 kilometres, is everything the chain still has to say. Within that great arc of stone and water, the conveyor belt story held almost perfectly for decades. A fixed flame, a moving plate, a bend that marked the plate's change of direction. It was, as scientific explanations go, one of the most elegant the earth sciences had produced, verifiable, predictive, grounded in physics, and beautiful in the way that simple explanations of complex things are sometimes beautiful. And the depths of it were staggering, once you let the physical scale of what Morgan proposed fully arrive. The Hawaiian plume, in his model and in the models that followed, was not a shallow phenomenon. It was not a quirk of the upper mantle, not a shallow pocket of unusually warm rock sitting a few hundred kilometres beneath the crust. The imaging of the mantle using seismic waves, the method that reads the interior of the Earth the way a CT scanner reads the interior of a body. Using the speed and direction of waves generated by earthquakes suggested something much deeper. A low-velocity anomaly, a region of warmer, less rigid rock, tracing downward beneath Hawaii through the upper mantle, through the transition zone, and into the lower mantle. Deep, possibly all the way to the core mantle boundary, roughly 2,900 kilometres below the ocean floor. To hold that image, a column of rock rising nearly 3,000 kilometres from the boundary between the planet's rocky outer layers and its liquid iron heart, ascending through layers of mantle whose pressure would crush any human object instantly, flowing upwards so slowly that the journey takes tens of millions of years, arriving beneath the Pacific plate, melting, erupting, building islands, and then watching those islands drift away while the column continues to rise. The Hawaiian plume, if this picture is correct, is one of the longest continuous structures in the planet's interior. A thread reaching from something very close to the Earth's iron core all the way up to the rocky skin that carries the ocean. The seismic imaging of the deep Hawaiian plume is, to be fair, more complicated in practice than in description, and this is worth holding on to for later. The images are not perfectly clear. The lower mantle signature of the plume has been debated in the imaging literature, and not every seismologist reads the pictures the same way. But the general picture, a deep, narrow, anomalously hot column feeding the Hawaiian hotspot from well below the upper mantle, became the foundation on which Morgan's plume model rested, and for the purposes of understanding the chain, the essential point is the depth. The plume is rooted deep. Deep enough that it was thought to be insulated from, and indifferent to, the plate tectonic forces operating in the shallower parts of the Earth. The plates moved above, the plume stayed below. This is what made the fixed hotspot assumption so natural, so defensible, so lasting. The plume was not a surface thing. It was not caught up in the same shuffling and reorganization of the upper mantle that drives plates around. It came from a different layer entirely. And so the assumption was that it stayed put, and everything that moved above it. And the chain was the record of that motion against a fixed point. The chain as instrument, the hotspot as anchor, the Pacific plate as the thing being measured. This was the picture, simple, powerful, and for a long time entirely satisfying. But here is what makes that picture not quite complete. Here is where the story, if you stay with it long enough, begins to show a seam. If you look at the Emperor Seamounts, not the Hawaiian Ridge, but the older northern limb of the chain, the one that runs nearly north-south, and you ask the question of where each seamount formed when its lavas first cooled, you are asking a question that the rock itself can answer. Cooling lava locks in the direction of the Earth's magnetic field at the moment it solidifies. The iron-bearing minerals in basalt act like tiny compass needles, aligning with the planet's field as the rock cools through a critical temperature called the Curie point, and then freezing in that alignment permanently as the rock continues to cool below it. The angle of that frozen alignment, specifically the angle of dip, the way the field lines tilt relative to horizontal, depends on the latitude where the rock cooled. Near the poles, the field is nearly vertical. Near the equator, it is nearly horizontal. At latitudes in between, the dip angle tells you, with reasonable precision, how far from the equator the rock was when it solidified. This is paleomagnetism. It is, in essence, a latitude record written in stone. And each of the Emperor Seamounts, drowned as they are below the surface of the Pacific, carries inside its lavas this fossil record of the latitude where it formed. If the hotspot had always been at roughly the latitude of Hawaii, about 20 degrees north, then the Emperor Seamounts, which were built over the same hotspot, should record formation at a similar latitude. That is what the fixed-hotspot model predicted. The Emperor lavas should show a paleolatitude consistent with the current position of the Hawaiian hotspot, adjusted for any motion of the entire Pacific plate relative to the Earth's rotation axis, a slight but real correction that paleomagnetic measurements can account for. And that is not what they show. The Emperor lavas record formation at paleolatitudes significantly north of where Hawaii is now. Not by a small margin, by a substantial one. The oldest Emperor Seamounts carry a paleomagnetic signature suggesting they formed 10 or 15 degrees further north of where the current Hawaiian hotspot sits, meaning that when those volcanoes were being built, the hotspot that built them was not at 20 degrees north latitude, it was much further north, which means the hotspot was not fixed. Not during the time the Emperor Seamounts were being built. Something moved. The question, as the decade of the 1990s gave way to the 2000s, was which something, and by how much, and what that meant for the beautiful, elegant story that Wilson and Morgan had constructed, and that 50 years of Earth science had built upon. That question was still open as the 21st century began. The bend in the Pacific floor sat on the seafloor, 60 degrees and 47 million years, as inscrutably patient as it had always been. And somewhere on the northwestern limb of the chain, in the deep-drowned basalt of Detroit Seamount and its neighbours, the answer was waiting. It had been waiting for 76 million years. In 2001, a ship stopped above that seamount, and people lowered a drill through 3 kilometres of cold black water. The drill had taken hours to reach the seafloor. 3 kilometres of water column, cold and absolute, and then the sediment. And then the first hard resistance of ancient basalt. The ship held its position on the surface, dynamic positioning, a web of thrusters keeping it stable against the current, while below, something that had not been touched in 76 million years began to yield, 1 centimetre at a time. But before we follow that drill into the rock, and before we hear what the rock said back, we need to walk the length of the chain one more time. Not the middle of it, which we have already travelled carefully, island by island, atoll by atoll, from the Big Island up through Midway and into the long, drowned column of the Emperor Seamounts. We need to go to the 2 ends, because the chain has 2 endpoints, and they are as unlike each other as anything you could place in the same sentence. One endpoint is being born. Right now. Tonight, as you listen to this. 30 kilometres southeast of the Big Island of Hawaiʻi, not a remarkable distance, less than the width of a modest county, less than an hour's drive on a flat road. There is a mountain that almost no one has seen. It rises roughly 4 kilometers from the seafloor, which makes it genuinely enormous by any terrestrial standard, but its summit is still approximately 975 meters below the surface of the Pacific. Nearly a full kilometer of ocean sits above its highest point. You could stack the Eiffel Tower on top of it and still not break the waterline. You could stack 3 Eiffel Towers and still have salt water above the highest strut. This mountain has a name. Its formal name is Kama-e-Whakanaloa, which translates roughly as the reddish child of Kanaloa, one of the major Hawaiian deities associated with the ocean and the deep. For most of its modern scientific history, it was called Meiji Seamount, and that name still appears widely in the literature, the way a nickname persists long after a formal name is restored. Most geologists still say Loihi when they are speaking quickly, the way you might use an old name for a place that has been formally renamed, not out of disrespect, but out of the stubborn habit of familiarity. Kama-Wakanaloa is the youngest volcano in the Hawaiian Emperor chain. Not young in the sense of decades or centuries, young in the sense that it has not yet existed long enough to build itself above sea level. It is a volcano in the process of becoming an island. The hotspot is beneath it right now, feeding it. Magma rises through the same conduit that has been building volcanoes in this chain for 82 million years, and it is building Kama-e-Whakanaloa upward, slowly, in darkness, at a depth where no sunlight has ever penetrated, and the pressure would crush an unprotected human body in an instant. In 1996, the mountain announced itself to the surface world. A swarm of earthquakes, thousands of them, in the span of a few days, shook the flanks of the volcano. Scientists monitoring the seismic network recognized the signature, magmatic intrusion, rock cracking, as molten material forced its way through. Surveys conducted afterward found that parts of the summit had collapsed, the caldera floor dropping in places by more than 100 meters. The volcano was rearranging its interior architecture, growing, the way volcanoes grow, violently, incrementally, completely indifferent to human timescales. Kama-e-Whakanaloa is the living demonstration of the hotspot. It is the current position of the flame beneath the plate. If you wanted to drive a stake into the seafloor right now to mark where the mantle-plume sits, Kama-e-Whakanaloa is where you would plant it. And like every volcano before it in the chain, like Kīlauea before its summit existed, like Kauai before its first rock broke the surface, like every drowned seamount that was once a high island, it will eventually breach the waterline. It will become an island. Over hundreds of thousands of years it will build itself tall enough for waves to carve its shores, for soil to form on its lava fields, for wind to carry seeds to it, for the same slow biological colonization that made every other Hawaiian island green. And eventually, if the tradition holds, for people to name it and live on it and give it stories. But that island does not exist yet. The next Hawaiian island is still a secret in the dark, 1,000 meters below the surface, growing upward at the pace of a patient geologic clock. And by the time it surfaces, by the time waves first touch its highest rocks, everything that we currently believe about the bend will have been revised again, overturned in some direction no one has yet thought to look, written differently in the textbooks of people we cannot quite imagine. The living end of the chain is being built in the dark. The dying end is being erased in the deep. At the far northwestern extremity of the Emperor Limb, there is a seamount called Meiji. Named for the Meiji Emperor, the Japanese ruler under whose reign Japan opened itself to the modern world in the 19th century. The naming convention for the Emperor Seamounts, applied by the American geographer Robert S. Dietz in 1954, reached for imperial grandeur, and Meiji, the name most associated with Japan's dramatic transformation, sits at the chain's most remote end, as if to mark the last known boundary of an explorer's map. Meiji Seamount is approximately 82 to 85 million years old. It was built by the Hawaiian hotspot during a time when non-avian dinosaurs still existed on land, when the Atlantic Ocean was considerably narrower than it is today, when the continents occupied arrangements we would barely recognize from any map we have ever seen. 82 million years is a number that resists genuine comprehension, no matter how long you sit with it. Meiji Seamount is currently being subducted. The Pacific Plate, moving relentlessly northwest, has carried Meiji to the edge of the Aleutian and Kamchatka Trench, the deep margin where the Pacific Plate begins its long descent beneath the North American and Eurasian plates. At subduction zones, the ocean floor does not simply stop at the edge of a continent. It bends downward, it slides under, it goes back into the mantle. The seafloor descends. The sediments on the seafloor descend. The mountains built on the seafloor, the seamounts, the guyots, the drowned remnants of former volcanic islands, they descend too. Meiji is at the lip of that descent. It has not fully gone under yet. Sonar surveys can still map its outline, still define its flanks, but in geological terms it is tilting toward the trench, and the amount of time remaining before it slides fully into the mantle and ceases to exist as a mappable feature is small. A few million years, perhaps, a moment, measured against the 82 million years it has already existed. When Meiji goes, it takes with it the oldest surviving evidence of the Hawaiian hotspot's work, the oldest direct record we have of what this flame was doing in the deep past. It takes with it a chapter that has no copy, no backup, no alternative archive. And older chapters are already gone. The hotspot was active before Meiji. It must have been, given that Meiji represents the oldest surviving link and not necessarily the oldest link that ever existed. But whatever the hotspot built before Meiji is gone. The seafloor that carried those older volcanoes has already been subducted, already returned to the mantle, already recycled into the slow planetary metabolism that continuously rebuilds the surface of the Earth from the inside. The chain may once have been considerably longer, older, more complete than anything we can now observe. We will never know what the hotspot was doing 100 million years ago, or 150, because the plate that could have preserved that record no longer exists above the mantle's surface. The subduction zone is a paper shredder. It has been running continuously for the entire lifetime of the chain, and it erases the oldest pages first, methodically, without mercy. This is one of the profound asymmetries of the geological record. On land, ancient rock can survive for billions of years, protected by the thickness and buoyancy of continental crust, which resists subduction, which stays at the surface no matter how many times the ocean floor around it is recycled. But oceanic crust is thin and dense, and wherever it meets a trench, it goes down. What is on it goes with it. The Hawaiian Emperor chain is not an 82 million year record stretching complete from one end to the other, oldest at one end, youngest at the other, the way a filing cabinet holds documents in order. It is 82 million years of whatever the shredder has not yet consumed. The archive begins at the point where the destruction has so far arrived. So, one end being built in the dark, one end being erased in the deep. And between those two endpoints, across 6,000 kilometers of Pacific seafloor, a story whose first chapters are already gone and whose last chapters have not yet been written. This is the chain, and for most of the second half of the 20th century, the chain seemed to tell a clean, satisfying, fully intelligible story. Let us sit with that story for a moment, because you need to believe it before you can feel what happened when it cracked. The story went like this. A fixed point deep in the mantle, the Hawaiian hotspot. A column of unusually hot rock rising from deep in the earth had been sitting beneath the Pacific plate for at least 80 million years, burning upward through the plate the way a candle flame burns through a sheet of paper being slid slowly over it. The plate moved northwest at roughly 7 to 10 centimetres per year, the rate a fingernail grows, applied across tens of millions of years. As each section of plate slid over the flame, the crust melted, erupted, built a volcano, built an island. Then the island was carried away. The volcano went extinct. The island began to cool, to subside, to erode. Over millions of years it became a fringing reef, then an atoll, then a flat-topped drowned platform, a guyot, then an invisible hump on the seafloor. Then eventually, nothing visible at all from the surface. Charles Darwin, working in 1842, had described exactly this cycle from observations of living atolls in the Pacific. He proposed that atolls form when volcanic islands subside slowly beneath the sea, the coral reef growing upward to keep pace with the sinking. He never connected it specifically to the Hawaiian chain, but he described the mechanism that the chain would later illustrate perfectly. The age progression was the evidence. Kīlauea, erupting now. Kauai, 5 million years old, quiet and deeply eroded by rain and wind, its sharp volcanic profile softened to gentle green ridges. Midway Atoll, 28 million years, just a ring of coral sitting at sea level with no volcanic rock above the surface. The former high island completely drowned by subsidence and planed by the sea. And then the seamounts, stepping northward and deepening, each one a little older than the one before it, all the way up the Emperor chain, past Suko and Jing and Detroit to ancient Meiji, tilting at the trench. And the bend, the 60-degree elbow at approximately 47 million years. Older textbooks said 43 million, but argon dating of the lavas at the elbow itself, at seamounts like Daikakuji and Kimmei, has revised that number upward to approximately 47 or 48 million years. The correction matters and is worth stating plainly, because the older figure of 43 million years still circulates in older sources and gets repeated without comment in articles that haven't caught up with the revision. The bend is not 43 million years old. It is closer to 47 or 48 million years old. And the difference of several million years is not trivial when you are trying to correlate the bend with other geological events that were happening around the same time. The bend, in the classical story, meant one thing and one thing only. The Pacific plate had changed direction. Sometime around 47 million years ago, it stopped moving the direction it had been moving and began moving in a different direction. The Emperor Seamounts, running nearly north-south, recorded the plate's previous motion, northward, more or less. The Hawaiian Ridge, running west-northwest, recorded the plate's subsequent motion. The elbow between them marked the moment of change. The hotspot was fixed. The plate had turned. The geometry of the chain was a record of the plate's motion. Full stop. This was, for decades, accepted as essentially the full answer. The fixed hotspot model was not just an explanation for Hawaii, it was a keystone of the broader framework of plate tectonics. Tuzo Wilson had proposed the hotspot idea in 1963 specifically to explain the Hawaiian age progression, and it was one of the ideas that helped confirm, in the early days of the plate tectonics revolution, that plates really were moving, that the seafloor was being created at ridges and consumed at trenches, that the continents were not static but carried by dynamic oceanic plates, that the whole surface of the Earth was in slow, continuous motion. Jason Morgan of Princeton extended the idea in 1971, arguing that hotspots were fed by narrow plumes rising from deep in the mantle, and used the Hawaiian Emperor bend as a primary example of how plate motion over fixed deep plumes could be tracked and measured. The model had predictive power. It agreed with independent paleomagnetic measurements from the Pacific Plate itself. It was consistent with similar age progressions observed in other island and seamount chains around the Pacific and beyond. It was, in short, not just one explanation among several. It was the explanation, and the Hawaiian Emperor bend was its most compelling piece of evidence. But there were hints, small discrepancies. The geometry of the Emperor limb, when examined with the increasing precision of later decades, was not perfectly consistent with the assumption that the hotspot had always sat exactly at Hawaii's current latitude. If you took the classical model at face value, fixed hotspot, plate turns at 47 million years, and you tried to predict where the Emperor Seamounts should be, they were close to where they actually are, but not quite right. The trend was slightly off. The discrepancy was not large enough to falsify the model on its own, not obviously enough to demand explanation. It was the kind of thing you could attribute to measurement uncertainty, to complexities in plate motion that the simple model wasn't capturing, to any of several technical factors that make geological reconstruction imprecise. So for most of the 1970s, 1980s and 1990s, it was set aside. Filed, not forgotten by everyone, but not the focus of serious investigative effort. The classical story was good enough, predictive enough, elegant enough to sustain itself against a small geometric discrepancy. And then came the drilling. Ocean Drilling Program Leg 197. That is the formal designation. It ran in 2001, part of the long-running international scientific program that had been systematically sampling the ocean floor since the late 1960s, lowering drill strings through kilometers of water to extract cores of ancient seafloor rock that no other method could reach. Leg 197 was designed specifically to address the question of whether the Hawaiian hotspot had been truly stationary during the formation of the Emperor Seamounts. The approach was direct and methodologically elegant. If the hotspot had been fixed at Hawaii's current latitude throughout the Emperor chain's formation, the ancient lavas should record formation at that latitude. If it had moved, the lavas would record a different latitude. The lavas would tell the truth, because lavas always tell the truth. It is built into their chemistry. The scientist leading the paleomagnetic analysis was John Tarduno, a geophysicist at the University of Rochester. His expertise was in paleomagnetism, the study of how the Earth's magnetic field is recorded in ancient rocks. He was, in the most literal possible sense, a person who read compasses frozen in stone. Paleomagnetism works because of a property of iron-bearing minerals in basalt. When basalt is molten, the microscopic iron-bearing crystals within it are free to rotate, free to align themselves with the Earth's magnetic field the way a compass needle aligns with magnetic north. This is not a metaphor, it is the same physical phenomenon. The crystals are tiny compasses, floating in liquid rock, pointing where the field points. As the lava cools and solidifies, those crystals lock in place, cemented into the surrounding rock matrix, frozen in whatever orientation the magnetic field imposed on them. At the precise moment, the temperature dropped below a threshold called the Curie point, the temperature below which the magnetic alignment becomes permanent. The rock solidifies around them. They are sealed inside basalt. Years pass, millions of years, tens of millions. The volcano goes extinct. Erosion planes it down. The plate carries it thousands of kilometers from where it formed. None of that motion, none of that time, changes the orientation locked inside the crystals. They point where they pointed the day the lava cooled. They have been pointing the same direction since the Cretaceous period. There is a detail that makes paleomagnetism so specifically useful as a latitude indicator. The Earth's magnetic field, while it does shift its polarity over geological time, reversing north to south, south to north, numerous times in the rock record, consistently behaves in a way that varies with latitude in a predictable manner. The inclination of the field, the angle at which magnetic field lines dip into the Earth's surface, is different at different latitudes. At the magnetic poles, the field lines plunge nearly straight downward. At the equator, they are nearly horizontal. At intermediate latitudes, they are tilted at intermediate angles, in a systematic, calculable relationship. A careful measurement of the inclination recorded in an ancient lava tells you with reasonable precision the latitude at which that lava cooled. Not the longitude. Paleomagnetism cannot tell you where around the circle of latitude the volcano sat, only how far from the equator. But the latitude it gives you is real. This was the tool John Tarduno brought to Detroit Seamount and Suiko Seamount, among the oldest in the Emperor chain. Detroit Seamount dates to approximately 76 million years. Suiko is younger, around 60 million. Both are fully submerged, their summits hundreds of meters below the Pacific surface, covered in decades' worth of sediment drifting down from the water above. To drill them, the Leg 197 team lowered a drill string through roughly 3 kilometers of water column and then bit into the hard ancient basalt beneath the sediment on the seamount flanks and summit. Drilling the deep seafloor is not like drilling on land. On land, gravity and the weight of the drill string drive the bit into rock. The mechanics are straightforward. On the deep seafloor, the drill string is a column of hollow steel pipe many kilometers long, hanging suspended in the water, its upper end connected to a rotating mechanism on the ship, while its lower end presses against the rock on the seamount. The ship must hold its position precisely, using acoustic beacons on the seafloor and a sophisticated dynamic positioning system. A network of thrusters firing continuously, making hundreds of small adjustments every minute, keeping the ship from drifting enough to bend or snap the drill string below. The North Pacific, where the Emperor Seamounts lie, is not known for gentle conditions. Oceanic swells cross those latitudes with nothing to interrupt them across thousands of kilometers of open water. The ship moved within its positioning tolerances, rising and falling on the long rhythms of the swell, and the drill string moved with it, and the science had to accommodate all of that. But the cores came up, cylinder after cylinder of ancient rock, extracted from depths where no light had ever reached and no instrument had previously gone. Dark basalt, fine-grained, dense. The iron-bearing crystals within it invisible to the naked eye, but detectable by the sensitive magnetometers in the ship's laboratory. The cores were cut, labelled, oriented. This last step being crucial if you lose track of which way the core was pointing when it came out of the rock, the paleomagnetic measurement becomes meaningless. Each sample was placed in a magnetometer capable of detecting the extremely faint residual magnetic field that the iron crystals, F, still retained 76 million years after they locked in their alignment. The magnetometer measured the direction and inclination of that frozen field, and the inclination, translated through the known mathematical relationship between inclination and latitude, gave the paleolatitude the latitude at which the rock had cooled. Tarduno and the team took those measurements at multiple sites, from multiple cores, at multiple depths within each seamount, because the last thing you want when you are about to claim that a cornerstone of plate tectonics is incomplete is to base that claim on a small sample that might have been locally disturbed or remagnetized by some later geological event. The redundancy was necessary. The statistical rigor was necessary. The result had to be unambiguous to be persuasive. The result was unambiguous. Detroit Seamount had cooled at a latitude significantly north of the current position of the Hawaiian hotspot. Not slightly north. Not within the measurement uncertainty. Not within the range you could wave away by invoking the imprecision of radiometric dating or the complexity of Pacific Plate reconstructions. Significantly north, approximately 10 to 15 degrees further north than where the Hawaiian hotspot sits today, after accounting for the overall motion of the Pacific Plate relative to the Earth's spin axis over the same period. Suiko Seamount showed a similar result. The implication was not subtle. If Detroit Seamount formed at a latitude significantly north of the hotspot's current position, and if Detroit was built directly over the hotspot when it erupted, which is the entire premise of the model, then the hotspot was considerably further north when Detroit was built than it is now. Not the plate in a different position relative to a fixed hotspot. The hotspot itself in a different position. The hotspot had moved. Not only the plate, the flame itself had walked. John Tarduno and his collaborators published these results in the journal Science in 2003. The Ocean Drilling Program Leg 197 paleomagnetic data indicated that the Hawaiian hotspot had been drifting southward at roughly 40 to 50 millimeters per year during the period when the Emperor Seamounts were being constructed. 40 to 50 millimeters per year, sustained across tens of millions of years. Over 30 million years, that rate adds up to something in the range of 1,200 kilometers of net southward displacement, comparable in scale to the distance the Pacific Plate itself moved over the same period. 1,200 kilometers. Hidden inside the orientation of iron crystals too small to see, in rock too old and too deep for anyone to have previously retrieved and measured directly. The answer had been there the whole time, sealed in basalt at the bottom of the North Pacific, waiting for someone to lower a drill 3 kilometers through cold water and ask. And the beautiful, clean story, the fixed hotspot, the plate that turned, the geometry that proved everything, had a crack running through it that could not be papered over or recalculated away. The thing the chain had been measuring against, the still point that gave all the plate motion its meaning, had itself been in motion. The plate's story was real. The age progression was genuine. The Pacific Plate was moving, had always been moving, is moving right now at the rate of a growing fingernail, dragging the Pacific Basin northwest across the face of the planet. All of that remained true, but woven into the same chain, expressed in the same geometry, was a second story, the story of the flame itself, drifting southward for 30 million years before settling somewhere close to where it sits today, while simultaneously the plate slid over it, and both motions combined in the same line drawn across the seafloor, indistinguishable from the outside unless you drilled into the rock and listened to what it had to say. Two moving things. One story. For 50 years, everyone had been reading it as one moving thing. That was what the bend had been hiding. And now, with that second story revealed, the central question: what caused the bend? What event at 47 million years had produced the sharp 60-degree kink in the 6,000-kilometre chain was no longer a single question with a single answer. It was a layered question, because now the bend had to account for two things happening at roughly the same time: the Pacific Plate reorienting from northward to northwestward motion, and the Hawaiian plume decelerating from its long southward drift toward something closer to stillness. Were these events connected? Was one a cause of the other? Were both of them responses to some third event that reorganized the forces acting on the Pacific Basin as a whole? And was the apparent coincidence of their timing, both happening around 47 million years ago, actually a real coincidence, a genuine simultaneous shift? Or was it partly an artifact of the uncertainty inherent in dating events that happened nearly 50 million years in the past? The scientists who had spent the previous 30 years using the bend as proof that hotspots don't move were not wrong to have done so. The classical model had been a legitimate and productive scientific framework. It had explained a great deal, accurately, and had driven an entire research program that produced real knowledge about how plates move and how the Earth's interior is organized. Wilson was not wrong. Morgan was not wrong. They had built a model from the best available evidence, and the model was powerfully explanatory as far as it went. But it hadn't gone far enough. The hotspot's own motion was not in the model. Because the data needed to detect that motion, the paleolatitudes preserved in 76-million-year-old basalt at the bottom of the Pacific hadn't been retrieved yet. The model was not an error. It was an incomplete picture that looked complete until someone found the missing layer. That is, in a sense, the most honest description of how science actually moves. Not by dramatic falsifications of wholly wrong theories, by the gradual revelation of layers that more complete data exposes. The bend was always more complicated than the textbook said. It just took a drill and 3 kilometers of cold water and the patience to read what the rock had written in its iron, to show how much more complicated it really was. The cores from Detroit's Seamount and Suiko Seamount sat in their storage facility. The results propagated through the geological literature in papers, responses, counter-arguments, revised models, and new questions. The bend in the Pacific floor remained exactly where it had always been, 60 degrees, 47 million years old, traced in dark basalt across 6,000 kilometers of Pacific seafloor from the living flame beneath Kama e Huakanaloa to the dying seamount tilting at the Kuril, Kamchatka Trench. The geometry had not changed, but the meaning of the geometry had deepened considerably. The question of what exactly had happened at 47 million years, what forces had shifted in the Pacific Basin and possibly beyond to produce both the plate's reorientation and the plume's deceleration, apparently simultaneously, that question remained open. It pointed outward from the chain, toward the broader geological context of the Eocene epoch, toward events happening in the Western Pacific and in distant parts of the world that might. through chains of physical causation we are still working to trace, have reached all the way to the bend in the Hawaiian Emperor chain. Those chains of causation and the honest uncertainty that still surrounds them were the next layer of the story, and they are where the argument about the bend lives today, in the journals, in the modelling studies, in the ongoing debates about what exactly reorganized the Pacific Plate and what, if anything, that reorganization had to do with the plume's own motion coming to rest. The flame was not fixed. That much was now known. What made it stop walking and what made the plate change direction around the same time, that was the question the rock had answered only partially. The rest of the answer was still being worked out, piece by piece, in the way that the best scientific questions always are, slowly, carefully, with constant revision, and without the clean finality that the textbooks tend to project onto things that are, in reality, still in motion. So let us follow that question where it leads. The numbers had come back from the laboratory, and they had not been gentle with the old story. The paleolatitude recorded in Detroit Seamount's ancient lava was far north of where the Hawaiian hotspot sits today. Suiko Seamount told the same tale. The stone compass, frozen inside those rocks, had preserved a magnetic signature that corresponded to a latitude roughly 1,000 kilometers or more north of the modern hotspot position, and the only coherent reading of that evidence was that the hotspot had not always been where it is now. Before approximately 47 million years ago, the Hawaiian mantle-plume had been drifting, moving southward. Slowly, by geological standards, roughly 40 to 50 millimeters per year, about the same pace as the plate above it, which gives you a sense of how modest those numbers sound until you multiply them across tens of millions of years and realize that 40 millimeters per year for 30 million years is 1,200 kilometers of travel. More than 700 miles. The flame had walked the length of a small continent before it settled. That is the inversion. That is the thing that the drilling ocean drilling program Leg 197, John Tarduno and his collaborators, the results published in 2003, had delivered to the scientific community after half a century of working with an assumption that turned out to be only approximately correct. The assumption was this: that mantle hotspots are fixed reference points, stationary anchors in the deep earth against which the motion of overlying plates can be measured with confidence. The Hawaiian Emperor chain had been one of the primary exhibits for that assumption. The age progression along the chain, so steady and so clear, had seemed to confirm it. Wilson in 1963, Morgan in 1971, the whole theoretical edifice that connected the chain's geometry to the plate's motion, all of it had rested, at least in part, on the premise that the flame doing the burning was staying put. And now the lavas themselves, speaking in the language of paleomagnetism, were saying it had not stayed put. Not entirely, not for the first 30 million years of the record. Before roughly 47 million years ago, the plume had been somewhere to the north of where it is now, drifting gradually southward, and the Emperor Seamounts, the northern limb of the chain, the ones running nearly due north toward Kamchatka, carried in their composition and their paleolatitude a record of that drift. The nearly north-south orientation of the Emperor limb was not purely a record of the plate moving northward and then turning. It was partly a record of the hotspot itself moving southward, which produces the same geometric effect in the chain, but for an entirely different reason. Sit with that for a moment. The same trail of dead volcanoes, the same steady age progression, the same geometry. And yet the meaning of that geometry had shifted fundamentally. Where before the Emperor Seamounts had redders, the plate was once moving roughly northward, now they redders. The plate was moving northward, and the hotspot was moving southward, and the north-south trend in the chain was the result of both motions occurring simultaneously in directions that happened to reinforce each other. Disentangling how much of the northern limb's orientation was due to plate motion and how much was due to plume drift required careful modelling, and those models are still being refined. The honest answer, the one the data actually supports, is that the Emperor limb's north-south trend probably reflects a combination of the two. And working out the exact proportions is one of the things that geological researchers are still doing today. This is where the modern verdict stands. Not at a clean single cause, but at a two-part answer, a genuine reconciliation of what had seemed like competing explanations. The bend in the Hawaiian Emperor chain, that sharp 60-degree elbow at approximately 47 to 50 million years ago, was produced by a combination of two things: the southward drift of the Hawaiian mantle-plume coming to a relative stop around that time, and a change in the direction the Pacific plate was moving. Both were real. Both contributed to the geometry you see on the ocean floor today. The question of their relative proportions, how much of the bend was the plume stopping, how much was the plate turning, is a question the scientific literature is still actively working through, with different research groups favouring different weightings depending on which data sets they prioritise and which models they use to interpret them. That is not a failure of science. That is science operating exactly as it should, in the presence of evidence that is genuinely ambiguous and genuinely rich, where the constraints are real but incomplete, and the work of narrowing them continues. The old answer, the plate simply turned a corner, was not wrong so much as it was incomplete. It had identified a real component of the truth. The new answer, the plume also moved, added another real component. The task now is to understand how those two components fit together in their correct proportions, and that task is still underway. What could have caused both things to happen at roughly the same time? What was going on in the Pacific Basin and in the broader world? Around 47 million years ago, that might explain why the Hawaiian plume's southward drift decelerated and why the Pacific plate reoriented its direction of travel. These are the questions that point outward from the chain itself, toward the wider geological context of the Eocene epoch, and they have generated their own body of research and their own unresolved debates. One candidate trigger for a Pacific plate reorganization around 47 million years ago is the initiation of subduction along what is now the Izu-Bonin-Mariana Arc in the western Pacific. This is a long curving chain of volcanic islands and underwater ridges that arcs through the western Pacific Ocean, south and southeast of Japan. And the geological evidence suggests that a new subduction zone began forming in this region sometime around that period, with oceanic crust beginning to sink beneath the western margin of the Pacific. When a new subduction zone begins, it does not start quietly. The foundering of cold, dense ocean floor into the mantle exerts a pulling force. Geologists call it slab pull. That is one of the most powerful drivers of plate motion. A new subduction zone opening in the western Pacific could have altered the balance of forces acting on the Pacific plate, potentially nudging it in a new direction. The timing is suggestive. Researchers who favor the plate reorganization component of the explanation have pointed to Izu-Bonin. Mariana subduction initiation as a plausible mechanism for why the Pacific Plate might have shifted its direction of travel around 47 million years ago. But suggestive timing is not proof, and the details of the correlation are contested. Getting the ages of subduction initiation to match cleanly with the age of the bend is harder than it sounds. And different studies have produced different estimates for when exactly subduction in that arc system began. The connection between the two events, the new subduction zone and the bending of the Hawaiian Emperor chain, is a hypothesis that many geologists find compelling, but it has not been definitively established. It remains, honestly, a well-supported idea in ongoing discussion rather than a closed case. The other candidate trigger that has attracted significant attention is the collision of the Indian subcontinent with Eurasia. This is one of the great geological events of the Cenozoic era, the era we are still living in, and it produced the Himalayas and the Tibetan Plateau, the highest mountain range and the highest plateau on Earth. The collision began sometime in the Eocene, with estimates ranging across a fairly wide window, and it fundamentally reorganized the stress environment across a large portion of the world's lithosphere. Some researchers have proposed that the collision's effects propagated through the global system of tectonic plates and contributed to a reorganization of Pacific Plate motion around the same time. The difficulty here is the word simultaneously. When we say that the India-Eurasia collision and the Hawaiian Emperor bend occurred around the same time, we are using the word same in a geological sense, which can mean within a few million years of each other. At human timescales, a few million years is an enormous span. At geological timescales, it is close enough to invite causal speculation, but not close enough to confirm it. The timing correlations between the India-Eurasia collision and the bend are, in the careful language that the dossier of evidence warrants, suggestive but not clean. They are part of the reason the bend's cause remains genuinely open rather than fully resolved. What emerges from all of this is a picture of the Earth's surface as something more like a slow conversation between different parts of the planet than a set of independent pieces moving without awareness of each other. A new subduction zone opening in the Western Pacific. A continent arriving at the southern margin of Asia after drifting northward across an ancient ocean for tens of millions of years. A mantle-plume somewhere beneath the central North Pacific, carrying heat from deep in the Earth. These events did not happen in isolation. The planet is a connected system, and forces generated in one place propagate, slowly, imperfectly, in ways that are genuinely difficult to model into other parts of the system. The bend in the Hawaiian Emperor chain may be the Pacific's record of some of those propagations. The exact causal chain is still being traced. And then there is the depth of the flame itself. Seismic tomography, the technique that uses earthquake waves traveling through the Earth to build images of what the interior looks like, in the same rough way that a medical CT scanner uses X-rays to image the inside of a body, has been used to look for the Hawaiian mantle-plume in the depths of the Earth. The results are intriguing, and they come with important caveats. Seismic images of the region beneath Hawaii do show a zone of relatively low seismic velocity extending downward from the hotspot, and low velocity in seismic waves generally corresponds to hotter rock, which is what you would expect from a plume of unusually warm material rising through the mantle. The images suggest this anomaly extends deep into the mantle, possibly all the way toward the boundary between the mantle and the iron-nickel outer core, which lies roughly 2,900 kilometers below the surface of the Earth. That is a remarkable depth. 2,900 kilometers down is nearly halfway to the center of the planet. The mantle itself is only about 2,900 kilometers thick, which means that if the Hawaiian plume is indeed rooted at or near the core mantle boundary, it reaches almost all the way across the mantle, from the very base of the rocky layer to within perhaps 100 kilometers of where the surface of the iron core begins. A flame that tall, by any analogy we might reach for, is extraordinary. It would make the Hawaiian hotspot not just a surface curiosity, but a feature with its roots in one of the deepest and most energetic interfaces in the entire planet. The place where the rocky mantle meets the liquid iron outer core, where heat from the core flows into the base of the mantle and drives currents that have been moving, in one form or another, for most of the Earth's 4.5 billion year history. The caveat, and it is a genuine one, is that seismic tomography of the deep mantle is hard. The resolution of the images degrades with depth because the signals are weaker and the paths the waves travel are longer and more complex. Different research groups, using different data sets and different imaging methods, have produced somewhat different pictures of the Hawaiian plume at depth. Some images show it as a continuous feature reaching to the core mantle boundary. Others are more ambiguous about whether the low-velocity anomaly is truly continuous or breaks up somewhere in the mid-mantle. The exact depth and continuity of the Hawaiian plume are, in the careful language of current science, still debated. What is not really debated is that there is something anomalously hot beneath Hawaii, extending well into the deep mantle. The precise geometry of it and how far it goes are questions where the imaging technology and the modelling are still being refined. But even with those caveats noted, there is something worth pausing on in the picture the evidence paints. A column of slightly hotter than average rock, rising from somewhere near the core mantle boundary, 2,900 kilometers down, and arriving at the base of the oceanic crust after a journey through the entire thickness of the mantle, where it melts and punches through the Pacific plate to build an island. The island grows, is carried away, cools and sinks, and becomes first a reef, then an atoll, then a flat-topped drowned seamount drifting slowly toward the northwest. And the process continues, one new volcano every million years or so, laying down a chain of evidence stretching 6,000 kilometers across the ocean floor. A monument built by a flame that has been burning, probably, for more than 80 million years, possibly much longer. Since the beginning of the record is erased at the Aleutian Trench, and the true starting date of the Hawaiian plume is unknown. That is the physical story. Clean in its outline, rich in its detail, genuinely open in some of its most interesting chapters. And then there is one more thread to draw in, before the story closes, one that does not belong to the scientific literature at all. But that deserves acknowledgement precisely because of how it has been carried, for centuries, by the people who lived on these islands and understood them in a different way. In the traditions of Hawaii, there is the story of Pele, the goddess of volcanoes and fire. Pele is not a metaphor in Hawaiian tradition. She is not a literary device or an allegory invented to explain geology. She is a genuinely sacred figure in a living culture, and her story is told with a depth and a complexity that no brief retelling can fully honour. But one aspect of her story carries a resonance worth noting carefully and respectfully as a coda to what the science has described. The tradition holds that Pele came to the Hawaiian Islands from somewhere to the north and moved southward through the chain, stopping at each island in turn, digging her fire pits, her craters, only to have them flood with the sea. She moved from island to island, seeking a home dry enough and deep enough to hold her fire, and she was driven from each resting place by her sister Enmakaukahi, the goddess of the sea. Island by island, southward and eastward through the chain, until she came at last to Kīlauea on the Big Island, where she is said to dwell today. The direction of that journey, from the older islands in the northwest toward the active fire in the southeast, runs exactly parallel to what the geology records. The oldest volcanoes are in the northwest. The youngest active fire is at Kīlauea in the southeast. The tradition holds that Pele moved from old islands to new ones, following the flame toward its current home, and the geology confirms that the flame has indeed moved, or rather that the plate has moved over it, so that the active volcanic center has shifted steadily toward the southeast over millions of years as the hotspot built new islands ahead of the chain's leading edge. This convergence is noted here as cultural resonance, not as corroboration. The tradition did not arise from geological knowledge in any technical sense, and it would be a misrepresentation of both science and culture to suggest that one confirms the other as evidence. What can be said honestly is that the people who lived on these islands, who watched Kīlauea erupt, and who knew the old islands to the northwest were no longer volcanic, carried in their stories a geographic truth about the direction of activity in the chain, and that truth happens to align with what modern science has spent decades and enormous effort uncovering. That is worth noting. It is a reminder that knowledge takes many forms, and that the human impulse to understand the landscape has never required laboratory equipment to produce real insight about the world. Pele's fire, in the tradition, burns at Kīlauea today. And in the geological reality, the leading edge of the Hawaiian hotspot today is not quite Kīlauea, but the seamount known as Kama e Wakanaloa, the name restored to what was long called Loihi. Still growing in the dark water, roughly 30 kilometers southeast of the Big Island, its summit still approximately 975 meters below the sea surface, invisible to anyone who has not gone looking for it with instruments. The next island, the one being built right now, in silence and heat and geological patience. On the same ancient schedule the chain has been following for 80 million years or more. It is not close to breaking the surface in any human sense. The mathematics of subsidence and eruption rate suggest that Kama e Wakanaloa will not become a proper island for something on the order of tens of thousands to hundreds of thousands of years. It will be built in the dark for a very long time before the first wave breaks over its rim. But it is there. It is real. It is the present moment of a process that began long before anything recognizable as a human being walked the earth, and it will continue long after any of our current landmarks have eroded and been replaced by ones we cannot imagine. And at the other end of the chain, simultaneously, the record is being erased. Meiji Seamount, roughly 82 to 85 million years old, the oldest surviving link in the chain, is currently sliding down into the Aleutian Trench, carried there by the same Pacific plate that built it, and then spent the rest of geological time transporting it toward its destruction. The ocean floor is moving at roughly the same pace everywhere along the plate, the fingernail's growth rate of 7 to 10 centimetres per year, and Meiji is being subducted as naturally and inevitably as everything else at a convergent margin eventually is. The rock that carries it will be reincorporated into the mantle. The seamount itself will be bent and compressed, and eventually dragged beneath the overriding plate and lost. Whatever volcanoes the Hawaiian plume built before Meiji, the chain's older history, the record of the 80 million years before the oldest surviving seamount, has already been swallowed and recycled. We do not know what that older record said. We cannot read it. It is gone in the most complete sense that geological history can be gone. This is the final quality of the chain that the narration wants to leave with you, because it is perhaps the most important one for understanding what this story is actually about. The Hawaiian Emperor chain is a record. It is a remarkably complete and detailed record of a process that has been operating for an almost incomprehensible length of time. But it is not a permanent record. It is being written at one end and erased at the other, continuously, and the portion available for us to read is only the middle section, the surviving fragment, from Kīlauea in the southeast to Meiji Seamount in the northwest, roughly 6,000 kilometers of testimony, representing something like 82 million years of geological history. Before that, silence. After Kīlauea, silence of a different kind, the silence of what has not yet been built, the future chain lying dormant in the still-moving plate, the volcanoes not yet born. What the scientists of the 20th and 21st centuries did with this fragment of record was extraordinary. They read the age progression and understood that the plate was moving. They identified the hotspot as the writing instrument. They built a theoretical framework, Wilson's 1963 hypothesis, Morgan's 1971 plume model, that connected a fragment of ocean floor testimony to the largest scale motions of the planetary surface. They used the chain's geometry to make arguments about the absolute direction and speed of Pacific plate motion. Arguments that fed into the broader revolution in understanding that plate tectonics represented in the second half of the 20th century. And then, in 2001, they took their drill ships to the oldest surviving seamounts in the chain and asked the rocks a question the rocks had been holding the answer to for 76 million years. The rocks answered. The fossil compasses in the lava said, "We were formed far to the north of where the hotspot is now." The plume was not stationary. It walked south for tens of millions of years at roughly 40 to 50 millimeters per year. And then, around 47 million years ago, it slowed. It settled into something closer to its current position. And the Pacific Plate, around the same time, for reasons that may include the opening of a new subduction zone in the Western Pacific, or the distant influence of a continent arriving at a new boundary, or some combination of forces not yet fully mapped, changed the direction of its travel. Northwest, where before it had been moving more nearly north. Both things happened. The combination of those two changes, encoded in the rock at the elbow of the chain, produced the 60-degree bend that maps have been showing since the first systematic surveys of the Pacific floor were conducted in the middle of the 20th century. The bend is not a single thing. It is the product of a conversation between two moving systems, the plate above and the plume below. At a moment 47 million years ago, when both of them were changing at once, in ways that may have been connected and may have been coincidental, and in proportions that the best current science has not yet finalized. That, in its fullest honest form, is the answer to what the bend is and why it was so hard to explain. The tidy version, the plate simply turned, was always a simplification. It was a useful simplification for a generation of textbooks and a generation of understanding, and it was not wrong exactly, but it was incomplete in a way that the rocks themselves could demonstrate once someone thought to drill into them and ask. The version that holds after the drilling is richer and more uncertain and more interesting. A wandering flame that walked south for 30 million years and then stopped. A plate that changed direction around the same time, driven by forces that may be connected to events in the Western Pacific and possibly to events on the far side of the world. A chain of evidence stretching from a submarine volcano still growing in the dark southeast of the Big Island to a seamount currently being swallowed by the oldest trench on Earth. A record being written and erased simultaneously, with us reading the middle pages of a document that has no beginning we can access and no ending we will live to see. The Pacific floor has been telling this story for 82 million years. The scientists began listening seriously in the 1960s. They have been listening more carefully ever since, with better instruments, more precisely dated samples, more refined models, and a growing willingness to revise the story when the evidence demands it. The revision that happened between 2001 and 2003, when John Tarduno and his colleagues published the results of Ocean Drilling Program Leg 197, was not a small correction. It was a fundamental reframing of what the chain meant and what it could reliably tell us. It did not invalidate the hotspot model. It complicated it, deepened it, made it more accurate, and it left some of the most important questions genuinely open. Where those open questions lead in the years and decades of research still to come is unknown. New drilling, new seismic imaging, new geodynamic models, all of these will continue to refine the picture. The proportions of plume drift versus plate reorganization at the bend will likely be narrowed. The triggers for the tile 47 million year plate reorganization will likely be better constrained. The depth of the Hawaiian plume and its continuity through the lower mantle will likely be imaged with increasing resolution as seismological networks improve. The story will be revised again in the careful, incremental way that the best science always is. But the core of it, the astonishing fact that the floor of the Pacific Ocean carries a 6,000-kilometre record of where a mantle plume has been for 80 million years, written in basalt and magnetism and the slow subsidence of ancient islands, that will not be revised away. That is one of the genuine wonders of the geological world. A record made in fire, preserved in stone, hidden under 3 kilometres of seawater, and readable with the right instruments and the right questions by creatures who arrived on the planet perhaps 3 million years ago and have been learning to read the Earth ever since. The chain is there tonight. The Pacific plate is moving over the hotspot at the rate your fingernails grow. Somewhere in the darkness southeast of the Big Island, 975 meters below the surface, Kīlauea is being built slowly from the inside out, pressure and heat and rising magma adding increment to increment in a process that does not hurry and does not stop. The active volcanoes on the Big Island, Kīlauea and Mauna Loa, are resting or stirring in the way they always have, shaped by the same source that has been shaping this chain since before the continents were arranged as they are now. Midway Atoll, 28 million years old, sits flat and coral ringed in the middle of the northern Pacific, the vestige of something that was once as tall and volcanic as the Big Island is today. Meiji Seamount, at the far end, tilts imperceptibly toward its destruction, carrying its ancient lava toward the trench that will swallow it, in what is the most patient kind of ending imaginable. And the elbow, the bend itself, at Daikakuji Seamount and Kimmei Seamount, approximately 47 million years old, sits in the deep ocean, unchanged by the centuries of argument about what made it. silent in the way that very old things tend to be silent. It does not know it was unexplained for 50 years. It does not know it was drilled, sampled, argued over, written about in journals, revised in textbooks. It is simply there, a kink in a long chain, the record of a moment when something changed in the deep earth, and the change was written on the ocean floor in the only medium the deep earth has available to it. Heat and time and rock. That is enough. More than enough, really, for one bend in one chain on the floor of one ocean. It was enough to occupy generations of scientists, to anchor a revolution in geological thinking, to survive a major reinterpretation, and to remain, at the edge of what we know, genuinely open. The questions at its edge are real questions, not empty ones. They point toward the interior of a planet that we have been living on for all of human history and that we are, still, only beginning to understand. Let that be a comfortable thought as you rest. The earth continues its work in the dark, at the pace of fingernails and floating plates, without requiring our attention or our understanding. The flame burns, the plate moves, the record extends. And somewhere in the quiet beneath the Pacific, the next island in the chain is being built, one slow increment at a time, for an ocean that will not see it break the surface for longer than human civilization has yet existed. You can put the question down for now. The chain will still be there in the morning. The bend will still be there. The debate in the journals and the conference rooms and the modelling studies will continue without you, which is exactly how it should be. Good science does not require an audience to proceed. It only asks, eventually, that someone come back and listen, and you have done that tonight. If something in this story settled differently for you, or stayed with you, the idea that even the fixed points might be moving, or the image of a volcano growing in the dark 1,000 meters underwater, leave it in the comments. These are the kinds of questions that are better carried by more than one mind. Tie off here at the Wisdom Docks. The tide will wait till morning.